All right, we are going to be starting with figuring out the contact forces on an inclined plane, namely, in particular, that normal force or the perpendicular contact force between the box or object that's on the ramp or hill and the ramp or hill itself. So let's get started thinking about how this whole thing is going to move. And keep in mind, sorry, I forgot to define this. The angle down here, theta, would be our angle of inclination or the angle at which the ramp is set relative to horizontal. Okay. So we know that if we were to just put an object on a smooth ramp with no friction, it would slide down the ramp. So we're going to think about forward as being directed down the ramp, which means we're going to need to tilt our axes. So instead of thinking about it as a horizontal axis and a vertical axis, we're going to think about it as an axis along the ramp and an axis parallel to the ramp. Okay. And we're going to have a perpendicular to the ramp and a parallel to the ramp one. So just keeping that in mind. Now, the normal force we're going to be dealing with is a force that is always perpendicular to the two surfaces in contact. Since the surfaces in contact are along the ramp, the normal force is going to push the box away from the ramp, making it go in the up and to the right direction that you see on the screen. We also are going to have the force of gravity, which is going to go straight down. And I'd encourage you to actually drop it all the way to make that nice perpendicular with our ground or the horizontal here. Now, when we have a force that's acting not on one of the axes, we're going to need to break it into its components, not its horizontal and vertical components, but its components that are parallel to the ramp and perpendicular to the ramp. But before we do that, we're going to need to figure out some angles here. We've made a right triangle, and that means we're going to have these two angles here add to 90 because psi plus theta equals 90. We've got a right triangle. The sum of the angles in a triangle have to equal 180. So if we want to break mg into components, we're going to need to know the angle here between the line perpendicular to the ramp and mg. And since that is a right angle, these two have to sum to 90, which makes that angle that we're looking at right here have to be equal to theta. Okay. So now that we have our angle, we can easily break it into part that is perpendicular to the ramp and part parallel to the ramp. Okay. The part of mg that is perpendicular to the ramp will be the part that I think of as holding it on or going into the ramp, while the component parallel to the ramp is the part that makes it slide, or, as you can see, is always going to be directed down the ramp. Okay. So if we're looking at this from a mathematical point of view, we would take our hypotenuse mg and the side that is adjacent is the perpendicular component, and that would make that value equal to mg cosine theta. While the component of mg parallel to the ramp, the part making it slide, is going to be the hypotenuse times the sine of theta, or mg sine theta. To make life a little clearer, or our diagram a little bit clearer, we're just going to pop those right there into the location. Now, do you need to write all of this out every time? No, but you will want to be able to write out at least this much to help you understand what's going on. Keep in mind that when you are writing in components, those component vectors need to be dashed. If they are not dashed, they're going to be thought of as a new additional vector, which is not what you intended. Thanks.